Welcome again. In the previous tutorial, we've done about the bpsk modulator. So in this tutorial, I'll just briefly talk about the demodulator. It's a little bit much, but the code is quite more understanding than the circuit. So I'll just touch it briefly. So what you have here is this is the input. They call it the ADC in. So whenever is where the signal is received into the circuitry, is it the ADC in? Then okay, I will start from there. Is received here then. So whenever is received through this ADC in, the first thing is it goes through the bit extension. That is, the MSB is extended. It's a total of 10 bits, but the MSB will be extended to make it a total of 18 bits. So this is how I extended it. I added extra 8 bits at the beginning and it took the value of the MSB. Then after that, it was multiplied with the NCO angle. One is for the sine, the other is for the cosine. So at this point, what you're trying to do is convolution, trying to mix it with this NCOI. I'll show you how these angles were gotten. So this NCOI and NCOQ, they were gotten using this sine submodel. When you go to the code, you see what they call sine root. Let me show you the sine root model and what it looks like. This is it. It's just a block of RAM that stores the sine equivalent from 0 to 254. So whatever value you put at the input here, we give you the corresponding sine output here. So you can watch as I'm changing it. It's moving around, changing from 1 to 254. So let me edit content. So this exactly what the table of this ROM is, a ROM I used. So this is like sine 00, sine 01, sine 02, sine 03, sine 04, sine 5, 6, 7, 8 till sine 255 because it's in hexadecimal. So these are not binary equivalent, they're hexadecimal equivalent. So that is how this sine ROM came about. So that was what we used when we were doing the demodulation, when we generated the sequencer, the values of those in sequencer. So here it was actually used again, so you can see. So after multiplying it with the input, the ADC in, you multiply it with the NCOI angle, and this NCOI angle were gotten by passing a counter that counts from 1 to 254, 5 through this sine ROM. So instead of getting 1, 2, 3, 4, 5, you're now getting the sine output equivalent, and that is what is called that NCOI, which was used to multiply the ADCC in signal. So here you can, here means it's just to say here says if is less than 255, just put the value into the sine and get the output here. This is a comparator that did that, and that's the comparator that energizes this multiplexer. Else subtract 256 from it and pass it through the sine submodel and now give us the output. So that's what basically happens up here. So you can see here this 0FF means 255. So it checks if it's either less than or equal to 255, take the normal, pass it through the sine ROM and give us the output. Else, subtract 256 from it and now pass it through the sine ROM and give us the output. So that was what was used to multiply our input ADCC in. So this was where the actual counter kind of was generated. Then again, so after that place, you have our mixer, the part where the signals were mixed. Excuse me. So let me briefly talk about the mixer. Now this is it. After the multiplication, after these multiplications, one is for the sine and one is for the cosine. The reason they did it for the two is because you will still check the two of them to get a feedback. If you add the sine and the cosine, if it's not equal to 0, then you have to subtract the phase. This is where the phase subtraction took place. Here, you can either add or subtract. So that is it. So down there, after the multiplication with the input, it was passed through a mixer. So let's go and see what a mixer does. Let me open the subcircuit mixer. So this is it. This is basically what it does. It adds all the data inputs together, and that is the mixing. It's more like an averaging. It's averaging it. So it adds everything together while passing the signal down, so you can see where the data comes in. After the multiplication, that data comes in here and starts going down from one RAM to another, from here to here to here to here. Because watch closely, don't look at the adders. The outputs of the RAM were fed into the next RAM. The output here was fed into the next RAM. The output here also was fed into the next RAM, and from here to the next RAM, all down. So that is how the signal mixing was done. After sending it down, they were all added at every clock cycle to give an output low pass filter of the sine. That's why they call it LPFI and LPFQ. This is LPFI. So it's more as like a moving averaging filter where you add all the signals together. So this is a moving average filter, kind of. This is the final mixer output here, and this is the filter output. So understand exactly what they do. The filter output does the adding, while the mixer takes the final output down here. So then again, so that's exactly what this mixing does. So remember that our data consists of the checksum, the magic number, and our main data. It was actually also received too. Okay. So at the end of the reception, everything goes in. At the end of the data reception, everything goes in to this data block here. So this is what actually generates our, remember the checksum where all the inputs were XORed together. So after XORing here, you get this checksum here, and then you will still compare it with the actual checksum received. So that is how this checksum serves as an error detector in the circuit. After receiving all the bits, an acknowledge bit is being sent, which finally transfers the whole bit out. It transfers, what's this? Let me correct something.